is KD for this reaction as written?
D double star over D.
Concentration of D double star over,
D star squared.
yeah, we'll just go ahead and put pressure here. And then, yeah. Does that help? Not really. Hmm? Somebody says square root. Does that make sense? Alright, I'm going to let you guys off the hook. I can't write this equation with that. If I did that, I'd have to go back through, and every other one of these would have to represent two sites on the surface. In other words, all these others would be squared. And this would not be squared.
Say that again.
The only way that you can do this is if you're doing a site balance on site pairs.
Oh, I see what you're saying.
You know,
you do star squared equals.
yeah.
So it has to be in relation to like the most amount of sites available?
It has to be in relation to, if I have something that occupies two sites on the surface, I can't arbitrarily sort of split it up within a denominator because those species aren't independent, right? They're attached to one another. So the only way that you can deal with this is by dealing with site paired species on the surface. Now a lot of times this detail it's not that important. And a lot of times this species doesn't mean you can't use Langmuir-Hinshelwood kinetics, because a lot of times those species aren't going to be the most abundant species on the surface. Yeah?
Now, if you just square them, would that count if you need two adjacent?
The adjacency would come into the pre-exponential factors. So there's ways of accounting for that adjacency, but they're not pretty outside the scope.
Your balance assumes that they're just randomly.
Yeah, no, they would show up. It would show up in the equilibrium constant. Which remember, those are typically measured. So if you're trying to do this from like a theoretical basis and calculating an equilibrium constant, you have to take into account that adjacency.
Right, so like if the CD is the one that's measured accounting for adjacency, then you
It's not measured accounting for adjacency. I'm saying that it literally will change the value of KD. You don't reinterpret your data, you just measure it. But I'm saying that requirement that you're mentioning will show up, but it's just going to show up in your measured value of KD.
But like don't you need to consider like how A, B, and C fill, so you know if you have adjacent spots for D.
But remember, he said experimentally,
Right,
by just
but like
measuring
that
it,
means
I
you
don't see any.
that means you need that KA to be found experimentally for this exact setup. You can't use the KA for a similar setup without T.
I know what you mean, and you're not wrong, but it's not usually an issue. Usually within catalysis, one or two species are going to dominate your surface, and that's it. But you're right that under those situations, and this goes outside of Langmuir-Hinshelwood assumptions, the most accurate way of getting those adsorption constants is measuring them within mixtures, not isolated. All right, let's talk about the one that you're actually going to see. Because this one's kind of a mess. This one, though, not nearly as messy. So how do I deal with this guy? First of all, why is that one not so messy? Because I'm making two species which both adsorb one species to one side. So now how do I account for it? Is that correct? No, so what do I put there?
1/2.
K KH2 is equal to H star squared divided by vacancy squared times the pressure of hydrogen, right? Remember, I want something here that represents H star, so I need to take the root of all of those things, and at that point you get 1/2. The 2's both go away, you get 1/2. At this point, it looks just like every other one that I could write, except of course the equilibrium constant and the pressure are raised to different exponents. But yeah, this is what you include. I think the last one we'll talk about. Yeah, it's gone forever. So imagine that this was a species that covers my surface, and it's made from and at these conditions, this is also true. So now, what species or what term do I put into the denominator to account for these species? Where should I start?
Is that all we're dealing with? It's just those two?
Yeah.
Oh.
No. I'm saying, yeah, you can have hydrogen on the surface. We already have hydrogen on our surface.
Right.
So now I'm adding another one, but I'm telling you that this is also true. That both of these reactions are taking place at the same time, and that both are quasi-equilibrated. So let's write down KOH. So what is the definition for that equilibrium constant?
H star, OH star, H2O. Well, H2O is a pure substance, right?
Not sure what you mean.
Never mind.
Just think, don't think about a liquid phase reaction. Water's not always a liquid. Think about steam.
Oh, it's gas. Oh, okay.
Yes.
Okay, then star squared.
Okay, and if I want to now get rid of the H star from this equation, what equation can I use to get rid of that H star?
KH star?
And KH2 is equal to H star squared. We just had this up. So H star is equal to pressure of hydrogen to the 1/2 vacant site divided by KH2 to the 1/2. So let's plug that into there. I left out something, but
K in.
In the numerator, just split each.
yeah, you're right.
Shouldn't be
Okay, so what shows up down here is OH star over star And what is that equal to, using that equation over there?
KOH, pH to star.
Stars cancel. Divided by what?
KH2 square root.
Sometimes you'll see equations, terms like that in the denominator. Let's think about that in the denominator for a second. What happens if I increase hydrogen pressure? What happens to the coverage of OH star? It decreases, right? And that makes sense. I'm putting in a source of hydrogen atoms, which pushes me back to the left within that equilibrated reaction. Now if I add water, the concentration of OH star increases or decreases? Increases, right? And again, that makes sense. I'm providing water, so I'm going to get more OH star on the surface. So this hasn't violated any of the rules of Langmuir. It just means that when you have an adsorption process, sometimes there's other reactions that can influence this adsorption's equilibrium, right? This is still an adsorption. I wrote this as a dissociative adsorption of water, right? Water comes down, it hits a site, 2 sites, and it dissociates. But I can't work out what is the concentration of OH without taking into account what is the concentration of hydrogen. Because they're related to each other because that reaction is equilibrium. All right, let's look now at the problem from the home. You said 10-4?